here together with Mette Ramsgard Thomsen. I'm very glad that personally that she's here. She's a very good friend and a very close collaborator of IAAC. This year she is also the leading faculty for a couple of workshops and a collaboration that we are doing in the research line of the digital matter intelligent constructions. Mette is a Danish architect. She's an expert in digital technologies. She's actually very much interested, and her research is focused between the craft and the digital and how this is changing architecture. And a few years ago, she is a professor in the Academy of Royal Arts, and she invented, and she is now directing a new department. Well, it's not that new, but how old is it, by the way? 8 years? Okay. The Department of CITA, Center for Information and Technology in Architecture, that it is a world-known department working on how the technologies of communication and information is changing architecture. So thank you very much, Mette, for being here for the lecture. Thank you for your collaboration. And yeah, the stage is yours.
Let me see if I can, yeah. Can we have a little bit more light? Because I like to, if it's complicated, then don't deal with it, but it's fine. But thank you very much for inviting me, and thank you for coming. It's really nice that I am here. I was also here, I think it's a year ago, no? A little bit more than a year ago. And it's really nice to be back. It's really nice to be back and work with you students. And I'm really, really happy that we're establishing this research program together, or exchange research, blah. I wonder if this is on, or... We have technology. Yeah, okay, it's on. Wonderful. So yeah, so it's really wonderful that we're setting up this collaboration, and I look very much forward to both this workshop and also the next one in March in Copenhagen. I've been thinking about that. I gave a lecture here not that long time ago, so I've tried to make sure that most of the projects are not the same, but some of them will repeat a little bit, just to be able to tell the story of how it is that we are looking at the research questions that we're looking at in CITA. Maybe first of all, what is CITA? CITA is a research center at the Academy in Copenhagen. We sit inside the architecture school, and what we look at is how computation is changing the way that we think, design and build architecture. So we're really interested in computation as a ground research question, as a way of thinking about how both the technologies of IT or technologies of architecture are changing, but also the culture of thinking. So how does it make us be able to do new designs, make new concepts, create a new world for us to build, to live in? So maybe the most sort of straightforward thing, that point of departure, is really that computation changes the way that we design, so it changes the scope of the design space, obviously through parametric modeling, through variable geometries. Instead of designing in an absolute space, we now design in respect to systems. And then, of course, there's a new relationship to the built. With computation changes the way that we address the material. So this sort of interlinking between the representational questions of architecture, maybe the side of our intellectuality as a practice, and then the material practices of architecture and how these things are connected, I think it sits absolutely at the core of architecture. This idea about how things are materialized is the key question for any architectural project, and that's why computation is at the center of architectural thinking and not something stuck on at the end as a new technology which just optimizes existing processes. So yeah, so we are often presented with computation in this kind of way, where like with the BIM models, it's just a way of optimizing, being quicker, faster, more precise with information. But I think there is so much more at stake around how computation changes and challenges the way that we are thinking. So I wanted to make 3 points today. I'll try to do them through projects, so through project descriptions. But the thread I want to follow is really how digital tools change material thinking, how digital tools introduce material design as part of an architectural design practice, which is actually a very different way of thinking about what it is that we do as architects. I know in our very small world, it seems like, of course it is, but if we go outside the walls of these institutions, then most architecture is done with prefabricated, catalogued materials. And inversely, how this material thinking changes or challenges the way that we think our representations, the way we think the digital model. So maybe a key sort of thought was when computation 15 years ago used to be a way that we escaped from the rail. So with virtual reality or mixed reality, then the idea was that the digital would allow us a new realm and we could go into the digital and leave our body behind. This, I talk about it in past tense, but obviously it's still a very well-flourishing idea, and gaming or Second Life or all of these kind of things could be ways of wanting to escape the physical. But I think that what's much more interesting about it is really that computation makes us think about the material in very different ways. And especially that materials are not something that is pre-given, but something that is active, pre-given and passive, but rather something that is active and something we can design and address and change with the way that we use materials in our designs. In CITA, we work with a practice-based research model. We work through installations and full-scale prototypes, and these are some examples of the kinds of things that we've been working with over the last years. Some of them are very straightforward, very implementable, very much addressed by straightforward questions of how architecture could perform, and some of them are very speculative and much more conceptual in their way of addressing what's at stake with these new technologies. Because of this sort of practice of always building things, testing technologies from the inside, which allows us to directly address and understand the creative practices of troubleshooting. I think all architects are very, very good at misusing tools. No? You understand a tool, and then the first thing we want to do is use it in another way than it was designed. And this is part of our creativity and also our individuality. Architects are different from each other. They have different kinds of practice. And by working with the sort of a simulated practice of creating and developing propositions, we are also engaged in this sort of creative practice of changing, challenging, reconfiguring tools. We also teach a lot, and we have a workshop practice in which we do these sort of 1 or 2 week intensives where we work with students with very precise questions. And we teach as we research. So often the two are connected completely, and often we'll come to students with questions which are very open-ended, we don't know what the answer is, or we'll come to students with something which we solved in a particular way. We'll share the tools that we develop, and we'll expect them to perform in the same way and change the way that we have created the solutions. We also, I think, yeah. As Areti said, we also now have a studio or a master's program attached to CITA in which we're looking at the same kinds of questions, and it's with this studio that we're collaborating. So maybe returning sort of to the three questions, perhaps the first question is really about what's the link between digital practice and material practice, and how can we start talking about digital material interlinking. And the way that we started these kinds of thinking had a lot to do with very straightforward fabrication projects. So we were involved in a series of projects. We were just looking at how do we create or change the interfaces by which we are understanding what it is that we're outputting to CNC fabrication, as you are very well versed in here. And when we were doing this, we learned very quickly that working for digital fabrication also learned incorporating crafts knowledge about how materials behave, because it's not a neutral thing to put a piece of wood into a saw. The saw will go through the material, and the forces within the wood will make the wood behave, will make it spring from each other. So we learned very quickly we needed to understand how materials behave and put these kinds of understandings into our models. This became a series of projects looking at active bending or material performance and trying to understand how we could harness this kind of behavior, which obviously, you know, is not new, is something we've been working as a practice as architects with for centuries, or throughout architecture. But how can we formalize these kinds of knowledges and put them into our representations? These are the new questions that are emerging. So in a Scandinavian context, working with material behavior has a lot to do with Aalto. But if I was from another end of the world, then working with material behavior, yeah, would have other kinds of resonances. This is hut building from Fiji. In Thicket and Thor, which are two projects very linked to each other, we were looking at trying to understand how we could encode the bending of wood as a way of creating a structural wall membrane. So what we were interested in here was understanding how digital crafting and the crafting of this sort of woven wall could become part of a digital strategy for building a membrane. So the project really relies on a very sort of standard or very sensitive tracing of the material, and just by bending and tracing here with a pencil on a piece of paper, understanding how the material is bending, and also what happens when we change the length of the material. So what is the performance of the wood? When does it snap? When can it no longer bend in respect to it? And then using this drawing to be able to inform a parametric model with the extrema of the structure. So, I'm sorry. Here, what's happening here is we're encoding the bending of the wood, and thereby being able to set up a system in which the bending of the wood is encoded into it, and then spitting out a set of worksheets which are then cut on a completely normal band saw, table saw, and then establishing these laser cut joints, which are about this big, which set the geometry, or the geometry of the bended sticks. So this one information, which is the bending of the joint and the length of the sticks, is really what is setting the whole structural whole. So all this variation is created from these two parameters. We did it again for the Lisbon Triennale, I think it's now 2 years ago. Yeah, 2 years ago, where we developed it again at 10 meters height. And I think at one level it doesn't really matter that you do it again bigger, but at the other side, you can say there's something that happens when your demonstrator or your prototype starts becoming the size of a building. It starts talking to you about what could this become if we were to engage directly in how we were to build an architecture. What was interesting in Thicket and Thor was really this idea of encoding the softness of the material. But what was also very naive about it, knowingly naive but still very naive, was that we were just bending one stick at a time. So in the digital model we only understand how one stick is bending. But of course we can very clearly understand that when we like in a fence, if we have many members that are connected and they're all soft, then the whole of the structure will have a very different performance. We cannot capture the bending of the whole of the structure by only knowing how one stick bends. We have to understand the aggregated behavior, the collective behavior of all the sticks together. So what was interesting about that was we then tried to use the nucleus engine in Maya to be able to simulate the connections between these materials. The nucleus is made for 3D. Let's hope. Come. No. For 3D simulation, let me see if I have it here. No, I'll just find it. Okay, well, I'm going to give up. But what we are seeing or not seeing is that the model together starts, we can then understand the relationships between the different members and start understanding that one material behavior has impact on the second member's material behavior, and that we need to think of these things as a whole. So maybe, or a sort of side question that came out of this was also the thinking that perhaps when we're working with these things, we need to rethink how it is that our representations actually function. So in the model for Thicket and Thor, we don't really have a geometric model. We have a relationship model. We understand which members are connected, and we understand where their connection points are, but we don't understand the actual geometry of all the bending. So this is very akin in logic to textile patterns. In textile patterns, when you create like a weaving pattern, a knitting pattern, or a lacing pattern, then you're less interested in a representation that tells you about the look and feel of a textile than you are in the diagram that really sets up the relationships of materials within the textile. So these kind of diagrams here are explaining to the weaver how the warp and the weft are actually meeting each other to create the pattern. So what's interesting about this is, again, this an understanding of the representation as a material encoding rather than a geometric description. So in shadow play, which is a project we did for the architecture house in Copenhagen, what we were looking at was creating a curtain that would filter the light in the space and take in a bit crappy quality, but take in the light in the space and create reflections within the space. I can't compete with that. So in shadow play is a 3D textile made in wood, It's a series of loop holes that are connected to each other, and each loop is then bringing forth the next loop. So it's like inspired by 3D textiles in the sense of 3D weaving systems, which really are about connecting a series of materials into masses. So not a plane, but a 3D mass of material. In shadow play, what we were doing is developing diagrams for understanding the material organization in the curtain, and then understanding all the design parameters and trying to variegate them as much as possible to get the greatest form of sort of deliberation within the design. We invented these tying systems that are using copper ties, small copper ties, which reflect the light and warm the light up. The whole structure is made of a 2 milliliter pine veneer, which is cut up, and here you can see the ties, and here you can see how every single loop is tied with these copper ties, which then sort of sit and shiver in the light. So what was interesting in shadow play was really this idea of trying to challenge the thinking or the logic of the design model. So rather than trying to draw the sort of outline of the building, then trying to understand the logic of the building or the structure that we're doing. So, of course, the key question in this is really how do we formalize the material knowledge within the model? So how is it that we can develop models or understandings of materials and put them in as input parameters in our digital models? In Dermoid, which we did together with SILE, the Spatial Information Architecture Lab at RMIT, and Mark Burry, I'm sure you are well familiar with, we did this 2-year collaboration which became Dermoid, which is we built it 3 times now, twice in Copenhagen and once in Australia. And the point of this structure, it's a very sort of idiosyncratic structure. There's a lot of things that are happening inside of it which are more or less logical for it, and it's also developed a lot through workshops. A lot of student workshops have sort of been structured together to make this this structural whole. What we were doing was we asked ourselves, how could we create a large span with short members? So timber gets more and more expensive the longer it is. If we can use short members, then we can save a lot of resources within the structural making. So in this structure, we're using what's called a reciprocal truss frame system, which is the idea that members can lean on each other and create interdependencies. So you get this triangulation within the network. So I think I talked about this last time also, I remember now. But I think if you can imagine that 3 people can sit on each other's lap, if you sort of imagine that. So as a structural system, you're creating a woven interdependency, and this is then being looped together in a network of sort of 3 people sitting on each other's lap. It's not really this reciprocal truss frame system, because what we're doing is we're lifting it out of the pain of gravity. So up here you have gravity in the right direction, so yes, it is reciprocal, but of course if you take the 3 people sitting on each other's lap and turn them out of gravity, they will fall down. No? So you get this. So it's more a system, again, a logic for material distribution than it is really a reciprocal truss frame. What was interesting here is that it's a space frame. Each member has is a dual structure. It opens up into this sort of cushion, which is then linked into the next cushion and woven back in together again. And you can see this sort of slightly weird zip connection, which is then being pressed together. So the whole thing is actually tied together. There's no glue in the construction at all. What we were doing here was trying to invent strategies for being able to design this kind of cushion. How would we be able to design the whole, and what kind of input parameters could we design for? So us being only architects in the start of this design process, we were really excited by the idea of that we would have many design parameters. So we parametricized absolutely everything. You can see the sizes of each of these triangles is changing, the thickness of the material changes, the size of the center member changes. There is nothing that is not changing. The width of the bar is changing, and the height of the top bar is changing also. Later, when we worked with engineers, they thought we were absolutely mad, and also maybe we were. One of the central conclusions was we thought, if we change everything in the material, we'll get a lot of variance in performance. But in reality, the solution of the single member is less important than the solution of the entire structural whole. It's a very, I think, important lesson to understand. So what we're doing here is we're understanding, I think I'm very unlucky, but we're inflating the structure, so we're putting, like a soap bubble, we're putting air into it, and as we do so, each of these tiling members here are redistributing across the surface and dynamically exchanging with each other, finding their right size. So we use this design process to be able to distribute the material across the structure. Sorry?
I want to see this.
Yeah, I know, I'm sorry. Maybe at the end, if you're still here, I'll find them all. In the second version of Dermoid, which we did for the Design Week, Copenhagen Design Week, literally a couple of months after having done the first one, we worked with engineers in Germany, Christoph Gengnagel, who is at the UDK in Berlin, and trying to understand how we could integrate FE, so finite element analysis, as a way of being able to understand the performance or predetermine or pre-analyze the performance and understand what the structural whole would do. So we built it here for the garden of the Copenhagen Design Museum, which is this very beautiful old hospital and a very sort of formal garden in which we sat the structure. And what the first strategy for this was we came from this wrong idea that it was really the performance of the single cell which would have most impact on the structural performance. So we here made this Efi analysis of the single element and tested it against a physical model. So we understood we could create drawings which anticipated how the structural model would work, and then we would be able to test them in physical world, and then from these single element analysis, we could put them together and understand the structural whole. So here we are understanding how the structure is actually performing, and what is, you can see that it's deforming here under stress. What is happening when you put weight onto the structure? And here fabricating it again in the beautiful spaces there, when it sits in the garden and hugs a tree. Let's go through the structure there. What was also interesting was that we then, at the end of the project, 3D scanned it, which then gave us an understanding of what we were actually building. So if we start thinking about design as an intention, analysis as also a kind of intention, a way of thinking about what do we expect our structures to do, and then the 3D scan as a way of correlating that with what actually happened, we can start establishing very good dialogues between what the digital model is doing within the design space and what the physical model or physical prototype is doing in the real space. And we can correlate and thereby evaluate our design processes. So yeah, comparing our expectations between one and the other. In Dermoid 3, which we just did last spring, what we were looking at here was we were trying to understand, so coming back to this idea of the analysis had in a way been misinformed by this expectation that the single elements would be the most important in the structure, then we, in the redesign of the structure, decided to make an Efi analysis at the structural whole level, so the level of the structural whole, trying to understand what the performance of the structure would be and how the performance of the structure changes during the inflation process. So here you can see also the way that we're designing is we're designing a flat topology and inflating it with air, and we can then see as it's distributing, it's informed with the structural knowledge of where the stress will be most acute. And here building is in the RMIT Design Hub, which is this very strange gallery, which is like 7 meters high, or 14 meters high and 7 meters wide. So you're walking around this cathedral of a thing. A second thing which was very interesting was a question about how we could skin the structure. So of course this is a very abstract project. It looks at how to construct a structural whole, but it is not really looking at how to make an architectural building envelope. But here we were interested in using knit as a material to think about skinning strategies. And I think it's a very good way of starting to discuss what these kind of structural exercises could be within a research environment by letting them start to become multi-material. The skinning of it was inspired by a series of textile experiments that I've been doing over the last 5 years, using CAD/CAM knitting to be able to create very specific patterns which are also individualized. So each pattern is different for each cell, because of course each cell is also different. And we're then generating these kind of colored diagrams here, which are really informing, the colors are code, informing the CNC knitting machine and feeding it and producing the material. And here developing design strategies, and here creating the sort of whatever prototypes for how the skinning could be happening. So, here. So the second question I wanted to ask was really how the digital tools introduce material design as part of an architectural design practice. So what happens with this idea that when we become the designers of materials as well as of the artifacts that they build? And of course, what's happening with computation is that we can address another level of complexity. It is not really that it's a different kind of manufacture. The saw is still a saw, the milling machine is still a milling machine. But with combining it with computation or computational steering, then we can just do more. So we can do more levels of detail and greater complexity within the design. I think the robot is different from that. But when we start looking at CNC in the fabrication, in industry, outside of the robot, then most of these tools that are computer controlled are traditional machines that are just being optimized by adding computational control. The robot is different because we can start developing new tools, and we can start thinking about how it is that we're actually creating or manipulating material in a very bespoke way. So this idea of the sort of universal openness of the robot is very interesting, I think. But anyway, so this idea of the new degrees of complexity also allows us to think about materials as being part of this level of design. And I think a very interesting model for thinking about computational strategies for material design lies with the advanced sale industry. And this slide here shows how 3DL Kevlar sails are designed. And what's interesting is this similar relationship. You have a set of simulations that are simulating the wind moving into the sail. It gives you a series of stress factors so you understand where the material is under most pressure. And then this informs the making of a bespoke sail. So what this is up here is a robot head that sits on this material which is being created on this huge form, which is also robotically controlled. So it's a table which is three-dimensional, and then we can then control the laying of fibers, these fibers here, in direct relationship to the simulation. So this idea of site-specific or use-specific materials is very well shown that it's absolutely part of our practice. Now this is very expensive and very high performance and exotic in some ways, but if we look to other kinds of practices, for instance the petrol that you put in your car, the washing powder you put in your washing machine, all of these materials are also highly designed materials. So in reality we live in a context where everything we're looking at is, or everything we are addressed by is more and more informed by very, very sharp design criteria. In architecture, I think there is a question about why we should work with these kinds of very light materials. And I think weight in buildings is also very, it has a lot of functionality. Weight gives stability, insulates sound, insulates heat. There's a lot of functionality about heavy buildings that we should not ignore. But at the same time, if we start thinking about the economy of fabrication, and maybe especially in our time, the economy of transportation, then this lighter building practice starts having new dimensions. And then the question that Bucky Fuller asked, sort of flippantly, "Madam, how much does your building weigh?" gets another kind of context. He was not asking this because of lighter buildings in that sense. This was all about military deployment and going out and invading people. But it's a different context for thinking about this, but I think the same kinds of questions become very important for us. And this idea that materials could vary through the structure. So we could have materials that at one level were very thick and strong, and then just gradually become weaker or more flexible or attain other properties across the material rather than having to shift between materials becomes interesting. A project that looks at this is the Composite Territories project done by Paul and Martin at CITA. We're looking at composite or fiber reinforced plastics as a material for design. And what I think is interesting here is really they're engaging in a material practice of trying to understand how can I build with fiber reinforced plastic, but it actually challenges the way that the design model itself. So what they're doing here is it's a little installation in a gallery in Copenhagen, and they're creating this sort of structural surface and really looking at how we could work or design with active bending. So normally when we work with materials, we'll put the bending in the joint. So we'll have a stiff member, bend, stiff member, bend, stiff member. And what they're looking at is, could we also work with many material parts, but could we add them together and put the bending into the material? And what's exciting is, of course, that this one is bending much less than that one. So we have different performance requirements for the material located at different places in the structural whole. The material here is this sort of tape of pre-made resin composites. So the fiber and the resin is already laid in the tape, and then we heat bind them together, actually with heat presses. So we press these sandwiches together. And I think we went from something like 20 layers to 5 layers or something. We were working on it endlessly, everyone, making these sandwich supports. Of course, the context for thinking about materials as being variated is being developed a lot in other industries, really trying to understand that there are different hierarchies or different performance criteria within the structural whole, and that we can generate seamless or define surfaces within one surface that is continuously varying in how the composite is actually made. So the composite system is continuous, but all the time changing. In Paul's and Martin's project, what they're doing is they're then creating this table, and this table then allows us to understand that there are materials that are very stiff up in the top left, and materials that are very weak in the right bottom, and then actually creating that as a lookup table that is then interfaced with the digital model, so that the digital model knows to move forth and back between the intentional model, like what is it that we want to design, and then understanding how, when we deploy these kind of materials, how is it that the material is actually bending. So you get this strange loop between intent and material realization, where you're continuously having to ask or simulate the behavior, ask the behavior of the model, and then re-inform it with your intention. So you're constantly designing forth and backwards. And here also we are 3D scanning it to understand the difference between what we thought we were building and what we built. And you can see there are moments of quite a lot of discrepancy up here and up in the top of the arch also. So this video I should have. Yeah. So one of the key questions that I think is emerging from these kinds of projects is really, how do we structure the organization of our models? Right now we sit within the 3D modeling and parametric modeling paradigm. So we understand our models within a 3D space, and we can set up parameters or variables within this design space. But these kinds of loops between design intent and material behavior might start asking new questions to what kind of system underlay we need to build, or logics we need to build, to be able to understand how connections can be made within the material. So what we're looking at here is a project called Lamella, again by Martin, where he's using swarm-based logics to encode how a series of wood elements might meet each other and create a vault. So the project is based on Sollinger structure. The Sollinger structure was a structure developed in the start of the last century in Germany, where there was a great shortage of building materials after the war, First World War. And here again, the point is you can build large arches with short members. So you're again weaving it together into this sort of structural whole, creating interdependencies between the members. And when we build in Sollinger structures, normally they're very regular shapes because all the members are the same length. So you can make a very beautiful vault like there. But when we start using computational systems, we can start varying the length of each member and the direction of each member, and thereby creating other kinds of formal logics of the whole. The project examines reciprocal truss frame systems and tries to understand the logics of how these kinds of connections can be made. Because, of course, if you want, you could just have a sort of initial shape and then sort of project these structures onto each other. But what then happens is that you get these discrepancies in how the system is actually meeting each other. So instead of coming from a sort of top-down version where you're implementing the elements onto an established digital surface, what's here happening is that we invented a series of agents, and each agent is a cell within the structure which then knows how to extend, to turn, or to twist and to turn itself to meet its partners. There's a series of compromises in this project which are very fundamental to the structure. For instance, in a normal swarm-based system, you have no understanding of your neighbor. You don't know where your neighbor is, or the only thing you know is where your next door neighbor is, and you could be close to anyone in the flock. But in this project here, each cell is named, and each cell will always meet the same neighbors. So you could, there are things that make it not so swarm-like, but it uses these same kinds of rule sets to be able to deform the base geometry and thereby create the structural whole. So I showed you that video. This was then built for an exhibition we did in Oslo, again using Efi Analysis to understand the structural performance, and then creating, using existing large-scale CNC fabrication to cut and detail the individual members. And what's interesting here is that when we're creating these very different geometries in the joints, we're doing it through the actual manipulation of the material. So the actual direction of the joint is happening through the CNC milling of the head of the structure. So, and here you have the final sort of expression of the form. So I think a key thing that we are continuously coming back to is this relationship between the structural whole and the material performance. And I think we're in a very interesting place right now in our design culture, because we have a very, very good understanding of what's happening at this level here, but we're now meeting it with a new emergent understanding of what's happening in this level here. So we can start marrying relationships or finding relationships between what's happening at the structural whole at the macro level and then what's happening at the micro level. And these kinds of knowledges are really coming from a whole series of different fields that are all around us. So material science, chemical engineering, all kinds of biomimicry engineering, all of these different kinds of practices are developing ways of modeling materials at micro level. And in material science, there's a great interest in this. It's called multi-scalar modeling. So this idea of modeling at multiple scales and interlinking them. And most often, it will work at 2 scales. So everyone has this diagram of macro, meso, and micro. And depending on your design practice, this can be very, very different things. If you're a chemical engineer, this might be the molecules, and this might be, I don't know, this could be the molecule, and this could be at nano level or something. It can happen at any scalar place. For us, obviously, it's most interesting to think of the structural whole and then the material whole. But the thing about all of this is that we have near to no understanding of how we can create feedback between these different kinds of modeling environments. So the ideal is that we can create models of the material and we can interface them with models of the structural whole as active parameters. So we can parametricize our structural wholes with these kinds of models. But at present, this is not really taking place. And what is very interesting, I think, also as a second detail, is that this scale in between is fundamentally architectural. We all know that the detailing of our buildings, the way we treat materials, completely has everything to do with how it is that we're building. So this sort of idea of the 3 scales is not abstract in our practice. It's something we are very, very close to. It's just that this new design sphere is really something that's only emerging right now. So I think this is the last project. I don't know how long I'm speaking. It's fine? Okay, good. The project I want to show here is the first project we've done within this sort of new framework of thinking, looking at new strategies for representation. And what we did was we said, let's look at growth as a design paradigm. And of course, you'll be aware of L systems. There's loads of digital models for how to model or implement growth within digital systems. And that's why we chose it. We thought, we know we can do growth, so let's think about how we can use growth as an active self-parametricizing way of understanding the parametric model. So what we were looking at was this idea that plants grow towards something, phototropism it's called, the idea that the plant seeks the sun. So how could we create a growth system which would be informing the growth of a structure? So we don't design from top down, but from bottom up. We define how the material is distributed, and then we let the structure grow into the world. So this is an exhibition piece we made for a project called, or an exhibition called Alive, which was designing with Alive systems in Paris last spring. What we were really interested in was this very interesting paper coming from biology, looking at how we can think about growth within a leaf venation. So within a leaf, how does the leaf actually grow these venation, or where the water is being pushed through the leaf. And it turns out that the way that this is happening is that there's a series of hormones that are being placed out into the leaf, and that then the venation grows, it traces these hormones and grows towards these hormones. And these hormones are called auxin. It's a really interesting paper if any of you are interested. So we started trying to create a leaf venation algorithm. This project's done by Martin and Dave and I together. And Dave has been doing the digital modeling. He's the guy who's coming tomorrow to work on the workshop also. And what he's here looking at is really trying to understand how he can place hormones or attractors into the space, design space, and then creating joinery or joints between, using them to create growing patterns between these hormones or attractors. So the RISE is a full installation, and in most of our projects, also the ones I've shown now, they always resonate with something. They are like a wall, or they are like a vault, or they aim to understand a dome or something like that. But in the RISE, we thought we would let go of this sort of typology and rather start thinking about it as a bush. It's really a connection of material, and it doesn't really want to create an architectural space as a direct implementation of the material system. So we're just trying to understand how can we grow something and how can we connect it. It's created in rattan, which is also the material we're working in with the workshop, and it's connected together with this HDF plast material, which is very interesting because it's both very soft and also very strong at the same time. So it allows for the deformation of the material. So coming back to the design system, what we started developing was this idea of the tropism. At one level, the phototropism, that we grow towards light, but also the idea of geotropism. Plants know that there's something called up. They don't suddenly grow the wrong way. They grow upwards. And also thigmotropism, so the idea of connections. So some plants are really good at connecting to other plants or connecting to themselves, as in this example here. Here's the rattan. If you are interested, please come up and look what we're doing with it. And then we generated these sort of combs for connecting materials. So we were interested in creating strands of materials or bundles of materials that connected many members together. And these CNC milled HDF plast material or roses were ways of making sure that they could connect all the materials together. Testing, figuring out how branching, of course branching is one of the key ideas in growth, that you grow and then you branch out and you grow forth. So what was the logic of branching within the structure? And how did when we are putting materials together, how does one material affect and change the bending of another material? So when we're connecting them together, they of course have this aggregate relationship to each other. Yeah. So I think this is also not going to work, but I have it here. Yeah. So what we're seeing here is the model growing. We have a set of starting points. The starting points are then growing towards the light. The light is simulated by this little circle in the ceiling. And as it cantilevers out, it shoots out these connector points, either connecting backwards towards the wall, this is the thigmotropism, or shooting off offsprings that allow it to connect back down to the ground. Let's see. Yeah. Then this model, which is generated through the growth algorithm, spits out information which allows us to be able to build it. Now, these bundles of material is all varied in different kinds of thicknesses, several material thicknesses, and also in a varying amount of members. So we had branches which had many members, and we also had branches with very few members. And this is then just being informed by the growth model. So we know how long things are and how much stress there is on it, allowing us to be able to understand the performance of the material. And here then the final 3D scan as an evaluation tool for how these things are being connected. Oh, interesting. And here you can see how the material is being distributed, again understanding how the material at one edge, when we have the two branches meeting each other, how does it actually affect the geometry of the whole, and how do we connect them together using the right kind of material to get the right geometry. And here, and some details. So, in a way, this project is very abstract because it doesn't have a direct relationship to a built structure like the Sollinger project does. It has a very clear relationship to what does it mean to build a roof. But in this model, we're really trying to understand what the logics of the underlying digital model could be. And I think what it still needs to do is to have a formal understanding of the material performance. So what we're doing here is we're encoding the material performance. We use it by actually tracing the material, understanding it through the set of diagrams. But again, it's an observational thing, it's an empirical thing. We look at the material as it's performing, and we're creating our own model. In a new project we'll be doing over the next year, we're looking at steel inflation, which is a project that Phil has been doing for a while at CITA, creating these steel cushions and inflating them with air. So what's very interesting about steel inflation is it's a one-way process. Once you've created the cushion and you pushed air into it, you can take it off the pressure, and it retains the deformation. But also what's very interesting about steel is it's a fully described material. So the engineers that we're collaborating collaborating with, we're just like, please, can we work in steel? Because then we can model the structures completely. And this is very different. When we're working with wood, we're working with very heterogeneous materials. Materials are often very different. It's different to where they're grown, how many knes, the knots in the wood there are, but with steel, we have very homogeneous understanding of the material. So what we're going to do as a next step in this project here is really try to understand how we can model what's going on at a material level and connect it to a model of what's going on at an overall structural level. So to create this multi-scalar strategy for design modeling. I think I won't bore you with the conclusions, as I think I've been telling them very clearly, but I think I like to end on also another practice of investigation. I think, of course, when we talk about these projects, they seem very linear, and they seem like we're going step by step by step, trying to understand problems in a sort of rational, linear way, which is true, we do. But at the same time, we're engaged in a whole set of other projects which I'm not always so sure where they land or what it is that they're informing us with. And I think this is very key to our practice, that we continuously engage and explore and speculate on how these kinds of structural and technological investigations change the way we think about architecture. So this is a set of drawings that I did as part of the Lisbon Triennale project, which really tries to draw what the spatial consequence of Thicket and Thor, the wall structures, could be. It takes the same kind of structural whole and draws it, but starts investigating what is the spatial nature of these kind of structures. And of course it does it in a sort of utopic way. It doesn't answer anything, but it's just asking questions. Also, how would it be to live inside a place which was built with these kind of structures? What is the spatial identity, and does it necessarily need to be a harmonic, nice place, or is it a little bit, this is a bit Batman-like, I think, the cave coming back to the home. Or here, a whole set of projects done on the sort of more poetic aspects of textiles as also part of a decoration. If we think of decoration not as something that is done to sort of paint over things that we don't quite know what are or whatever, but also part of our cultural heritage as architects, the imagining of the interior. So here this project was done as part of an architectural textiles project together with some craftspeople in Sweden called HV Lab. Looking at hand dyeing as a way of creating these very sort of soft interior, or a mountain landscape for the interior. And looking at heritage from people like Schinkel, who made these tent rooms in the 19th century. And you all know Schinkel, classicist, rational, you know, but he also created these very sort of exotic rooms here for Humboldt, who was a great German explorer who traveled across South America, and also for Queen Louise, the present Queen of Prussia, which have a very scenographic and very different kind of understanding of architecture as something lush, as something enveloped, as something rich with narrative and staging. And I think these kinds of other ways of thinking about what it is that we are developing with all our new technologies and how they fit into our built environment is really important. But at the same time, I also know that this does not fit into the big narrative of where it is that we're going. I just think it's very important to keep on working in a cluster of projects and not be so worried that everything fits together, and assume that even though I don't know really what this is about now, maybe I will in 5 years' time, or maybe things will start appearing from this that I hadn't anticipated. And we need to do that, I think, when we engage with technology. Otherwise, we hit this sort of rationalist side of things, which I think can be empowering for our culture. So, thank you very much. I forget this slide, but I also want to say that CITA is not me, and all of these projects are not me, but it's us, which is quite large. There's a huge host of people who are enveloped, and especially our interns, without whom we would never be able to build all these things. So please remember them. Thank you.
Through your presentation, I saw that it's obvious that more and more we're getting to know the properties of the material. And my question is, do you think if we are able to change those properties into codes or algorithm and really understand from where they come at the biological scale, if we are able to separate them, then are we far from being able to invent new materials by taking the different properties or parameters as codes, and like to suit a new material or to suit new situation independently of the materials, so create new materials from the different properties and of the existing materials?
I think it's a really central question, and I think the answer is very clear, yes. And I think but the reason it's so obvious is because it's already happening. It's just not happening in our practice. But if we look to things like the textile practice, or for instance, the making of I don't know, again, the example of the gasoline that we put in our cars, or the washing powder, then we are enveloped by practices that are creating very, very, very specific materials. So I went to a lecture a couple of years ago with a guy from Leverhulme who was telling us about the design of enzymes inside our washing powder, which could be a boring lecture, but was really, really interesting, because what he was talking about was the creation of enzymes that are able to understand contact with skin, so that when the clothes that has been washed in this washing powder touches the skin, then it releases perfume. So rather than perfuming everything in the world, you just perfume the body, because that's what you want to do at the end of the day. And so this kind of idea of creating smart materials that are working at a molecular level is all around us. And I think what we need to do as architects is understand, first of all, what is appropriate, what scale level is appropriate. I think personally that's why I've been working so much with textiles, because it works at the scale of the millimeter or the half millimeter, or it's not at this nanoscale where, of course, in architecture we work with nanomaterials also for creating coatings for glass and so on. But it's a little bit difficult for me as an architect designer to address these scales. So what is appropriate, and also what kind of practices are able to work with this. So that's also why the composite materials industry is really, really interesting, because it also affects something which is very direct, structural performance. So.
Thank you. Last year we were studying biomimicry in our master course, and we were also really into tropism because we had a material. And I was curious about the fact, like, how you actually digitalize the behavior of the leaves and how you transfer it as this system. Yeah. Like the tignotropism that you attach to the wall, okay, it's reacting to the wall, but what was the parameters? Because we struggled a lot in the beginning to, okay, we scanned these leaves, we recorded them, and we spent a lot of time to understand how these fibers behave.
I think if you want a detailed answer, Dave will come tomorrow, and I'm very sure he will show you the model and exactly what he's done. So please come and do that with him. But what we were doing sort of at a general level was really trying to understand, actually it's in the video best, isn't it? Was to understand how the structure, so we're setting off the growth algorithm here, and when the growth becomes too weak, you know, as it's cantilevering out, then it will shoot back. So the statement that means that it shoots back is when I cannot carry myself anymore, then I will search for a connection point, and I'll search for the closest connection point. But I think what is more interesting for you is really the modeling of the oxen. So trying to understand how we could emulate this or mimic the performance of the hormones in the leaf. And here we're using attractors, but I think you should talk to Dave when he's coming here. Cool. Yeah.
No, first of all, I want to thank you, Mette. It's always very, very exciting to see your work, because you have this talent to explain very clearly how the computational design not only changed the way we design, but also like started introducing other kind of aspects related with architectural construction, such as fabrication, or even the fact that we are now getting into the nanoscale of the materiality in order to combine this with our design. And it's a great variety of, I don't know if it's going to be a question or but it's my kind of thinking at that moment that all these kind of projects, that they have a variety of nature and detailing, I think helps understand in a way how you take into consideration the design environment as well. And those tools help you understand that it's different to design a sculpture that could be anywhere, and it's different to start figuring out this, to set up the rules so that you can respond to the specific environment. And I think that's amazing on all the projects that you are working on. But this is always making me thinking a step further, which I know it's complicated at the moment, but this is also part of my personal interest of how we can figure out design strategies and how we can manipulate the tools or invent new tools so that the materiality with which we're working with is not only informed by data that they are static in terms of physical geometry of our design space, but taking into consideration the environment that keeps on changing second by second. Now the temperature is changing second by second, humidity is changing, so there is a kind of parameters related with our geometrical, let's say, in physical space of designing. But the challenge, I think, is really getting into how we can use this technology in order to apply it in our design and combine it with materials, manage to have architectural outcome that is not rigid anymore, that is able to interact in a more dynamic way with our environment. And
even though it might not be a question, I would like to answer because I think it's really, really interesting point, because of course what I've been looking at here or showing you here is material simulation, but if we look at our simulation tools, there's a huge host of environmental simulation tools that we can work with, and you will know Ecotect, or you will know other kinds of solar modeling tools, for instance, of which there's a whole host of them. And we had a PhD student, an industrial PhD, working with 3XN, which is a larger Danish practice, on implementing lightweight sketch tools for early design stage of understanding solar relationships. So what is the heat gain, what needs for ventilation, how do we get as much light into the building as possible. And what was very interesting in this is really he was looking at the absolute start of the design phase. So when offices engage in volume studies and they just put a big block there and they twist it a little bit, that's anyway what they do with 3XN. So exactly. how do we connect them? No, so but the point is that our environment is dynamic, and that we have simulation tools that understand this dynamics. We just did a workshop with our students where we were using environmental simulation tools, and one of the students said, "Now I know why it should be moving." And I thought, but all the time the sun is moving, all the time we get this dynamic relationship. It isn't only with using these tools that we understand our environment is dynamic. So I think this interrelationship between simulation and material design is more multi-pronged than what I'm talking about here. And it is also something which sets up new questions. I think it's just not in these projects, but very important. But maybe we should have a beer. And I will be here for until Monday, and Dave is here until Wednesday morning or Tuesday afternoon. And it's really nice if you come and chat. Only fun. We're up there and later down here. Okay, thanks a lot for coming.